Okay, the 22nd question, that's from moment of inertia, and it has nice symmetry argument involved. Let me show what is the question. There is a triangular lamina and point D and E are the midpoints of AB and AC respectively. G is the centroid. The moment of inertia of this big lamina, the entire ABC, about an axis passing through G and perpendicular is I naught. That has been given. And then the question further says that this triangular plate, the smaller one, has been removed, and we got to compute the moment of inertia of the remaining portion about the same very axis. Let's see, beautiful, isn't it? For that, what we'll do is that we will have to use nice argument of symmetry. So let me start with a figure here to make it a bit larger so that you will get a nice visualization. And after that, let me draw the mid as well. So somewhere here is the midpoint, and this is that given point G, the centroid. Now just think carefully. What I will do is that in order to calculate the moment of inertia of the remaining portion, let me just go with some additional construction as well. So I will make 4 identical triangles in this way. So all these triangles would be identical in terms of mass distribution, not in terms of the positioning with respect to the axis. Now think very carefully. If I say the moment of inertia of this, which is I naught, I can easily equate it to K times MA square, where K would be a factor which comes in the coefficient and A is the side of the triangle. Whatever it comes, K, I'm not interested. Now see very carefully. Let me call this one, the central one, as plate 1, all right? Let me call that. Now you would say, well, the question has asked for this plate. That's fine. We'll do that. But initially, let's consider this one, the central plate, the triangular one. What would be its moment of inertia about the same axis G if I represent by I? Look, for any axis passing through the centroid, we have already said kMa square, where m is the mass of this big plate. Now this G is also the centroid of this given triangular plate, isn't it? That's how it comes. So how can we deal further? Let's try to see. For this plate P1, the moment of inertia is going to be something like this, I naught divided by 16. And why 16? Because the mass has gone 1/4, the length has gone 1/2, so quite obviously the moment of inertia will be I naught by 16. Whose is it? The moment of inertia of the central one about this point G. Now coming back to the original story. The entire plate, the moment of inertia is I naught, right? And that is the sum of moment of inertia of all these 4. For the central one, we have already said it is I naught by 16 for this. And for this, all will have the moment of inertia value identical about G. So let me call that by I dash. I dash is the moment of inertia of individual plate about G. Okay, that's a point. So we thought the entire plate to be made up of 4 such segments, and the total moment of inertia I naught about the centroid. For the central one, I naught by 16. Remaining, keep in mind, I dash is the moment of inertia of this plate about G, and they are all identical. So from this, what will be I dash? So I dash is going to be 5 I naught by 16. All right. Now back again to the same story. Now let's see another alternative viewpoint. Coming back to this, the total moment of inertia is I naught will be equals to the moment of inertia of this particular plate. You could see about the excess G is 5 I naught by 16, and the remaining one let me call as I dash. I dash is the moment of inertia of the remaining portion. That's what we need to calculate. So what do you get? The value of I dash, that's equals to 11 I naught by 16. And that has been finally done. The correct answer would be 11 because we need to compare in terms of n I naught by 16. So 11 would be the correct answer. Let's go to the next. The next one, question number 23. That's a very straightforward one, a closed vessel. So that means completely isochoric process, contains 0.1 mole of monoatomic gas at this temperature and 0.05 of the same gas at this temperature. They are mixed. We need to calculate the equilibrium temperature. Now let's just equate the initial internal energy with the final one. Initial, if you see, is 0.1 CV and temperature is 200. That will be the internal energy. And for the next, that's going to be 0.05. CV will remain same. Reason, the gas nature is same. And finally, what will be the total number of mole? That's going to be 0.15 into CV temperature T. We have just equated the initial internal energy with the final one, and that value comes out to be 266.67, the temperature in Kelvin. Let's go to the 24th question.